Francis. So for like this is the ideal tutorial. I will be like showing you guys a really simple code of ideal today, and we'll like discuss how to do things with ideal, how to like make plots mainly. So before starting, like you need to make sure that you have access to grid HPC, that is this one. I think you guys have the access in your grid, own grid, right?
Yeah.
Yeah. I
Okay,
think I'm
so that's good. And do you guys have Xming installed to your computer, like this one, this
Yeah,
icon
I
here?
do.
Yeah, I do.
Okay. Okay, so you can use the Emacs and ideal license. We all have ideal license in our grid HPC and the Globus setup, like this one, this Globus
Mm-hmm.
setup. So those are like the like pre-requirement for before even starting like ideal coding in ideal or making plot in it. So first of all, to like have you guys even ever like used the Emacs like this one?
I did once.
Okay.
Yeah, I think it's basically like the Vim, right? Like you're just looking at like code and edit and whatnot.
Yeah, it's a good like code editor. So we can also edit codes in our grid HPC, but like it's very convenient to uh, like use this Emacs, and like we can easily edit any of our codes here, and it will be saved in our grid HPC. So before calling Emacs, I'm gonna close this window, and I am gonna hit this Xming button, or you can do it manually, like search the Xming app and click on it. So it will start the Xming here, and then like can you can like start the putty source. Okay. So here by inserting our grid domain or host name, and this is the SSH. So three things to do here in order to start the Emacs. First, hit the button of Xming or start Xming. Then there is the SSH, and there is X11. So you have to enable the X11 forwarding every time you need to use the Emacs. And just like any other like login, you have to give our grid domain or hostname grid.win.edu and open. So I'm gonna log in.
Hey, Debitash.
Yeah.
So like when I had been going through Terminal with Luke a while back, he had me download what's called X Quartz. It's the same
Okay.
it's the same icon as the Xming that you're using. I'm not sure if it's the equivalent to that. But
I'm not sure because professor like told me to use Xming. I'm not sure if it's like X. What did you call it?
X Quartz.
Okay, so that might be the software for Mac. I'm not sure actually. So if it's the same icon, I think it does the same work or same function, I believe.
I have the same thing too. X
So
quartz.
so you to use Mac, right?
Yes.
Yeah.
Like okay. So I think that might be like the software for Mac. So you can ask Dr. Wang about that. I think the two softwares are like the different versions for Windows and Mac.
Mm-hmm.
So I have done that. I have hit the Xping button, and then I have like forwarded the X11, and then in warrior mode we have to call the Emacs. Just simply typing Emacs. So by simply typing Emacs, a window will open here, and by that way, this window, mm, this is the Emacs like home, and we can open any file, any like any kind of file actually in our grid HPC, whether it's like netcdf file or ACI file or our like ideal programs, any kind of, but this editor is, I use this editor for mainly ideal edit to edit the ideal codes. So there is my ideal codes, and I'm gonna show you how to plot the surface methane concentration. So this is the code. I will be going through the code just in a minute. Okay, so first of all, uh, there is only three major steps. First, we have to read the model simulation output files, which is in netcdf files, netcdf format, and find out the desired variables. Like I am focused on here methane concentration, the methane surface concentration of 2015 June. So there is this simulation output. Like if I go to simulation, my simulation directory, once like you run a global simulation, it will save some output files in netcdf format. So if I go to this, go to my running directory, you can see there is a output directory. So once I go in there, you will see this is the one, GEOS-Chem species concentration 2015 June. So this one means it started from the June 1st and ended in June 31st. So it's for the full month. So you can actually set the frequency of this model simulation output in input.geos or in the running directory actually. So I'm not gonna go there. Just this is the output file that we are trying to process, or this is the output file. So these are the concentration files, and this is the emission files. So HEMCO is designated for only emissions, and the species concentration are for concentration of different species. So in order to like read those files, how like the first step, read model simulation output files. How can we read them? So in order to read them, we have to load and unload some modules. Those are, we have to unload the grid default module, and we have to load the Intel 2019. We have to load the netcdf 4.7.1. We have to load netcdf Fortran 4.4.5, and we have to load the HDF 5.10.4, I think. So you can see the module list. Intel 2019, netcdf 4.7.1, netcdf Fortran 4.4.5, and HDF 5 1.10.4. So I think like you guys have tried starting a global simulation or any other simulation in your grid, right? Have you guys tried starting a simulation in your grid? Hello.
Hello.
Yeah.
Not exactly. I've just run. I've used Cheyenne. Um, so I'm currently in the middle of like simulation, getting all the running some of the data there, but not exactly.
Okay. So, Noribeth, have you tried starting a simulation in your grid or WarfCam?
I mean, I've done like some practice ones, but to be honest, like I wasn't really sure what I was looking for. That was like my big problem. Um,
Okay. So, I am not I have not worked in WarfCam, but for GeoS-Chem, we need to install or load these modules before starting any model simulation. So these are pretty same for before reading the output directory. So I'm not sure you use putty for your WarfCam or not. Do you guys use putty for your WarfCam or
no.
terminal? Terminal, I think terminal, right?
Yeah. Hmm.
So, yeah, I think all of our grids are similar. Just we are using different model simulations or different packages like WarfCam or GeoS-Chem. The basic grid HPC is similar, so they should be able to load these modules, whether you're using WarfCam or you're using GeoS-Chem. So after loading these files, we have to go to the output directory and write ncdump h. H is the header of these files that will print out the only headers of this file. Those files are pretty big for us to read, so we need only the header of those files. So I want to read the GeoS-Chem species concentration 2015 June. So this is the netcdf file, and I want to know the header, and the command is ncdump. So when I hit enter, it will come up with the header files. So you can see there is a different species like NO, ozone, PAN, carbon monoxide. There is a different species here. So we have to find out the methane one, as we are we would like to plot uh, the surface concentration of methane. So here there's somewhere in there. Oops. Just a second. Yeah, this one. So this is our variables and the info needed for our desired variable. So this is the variable, the main variable for species concentration of methane, and the unit, the current unit is mole per mole, and this is the one. This is one variable, and the other variables are, you can see, the lat and lon, which is latitude and longitude. So we have to we have to like read the dimensions or the size of lat and lon. The latitude is 91. It's the number of levels or the number of layers in this simulation. Those simulation ran for 91 levels of or 91 layers of latitude and 144 layers of longitude. So we know three things for from here: the size of the latitude and longitude, which is the size of the total plot, and the methane one, um, this one. So the methane variable is this one, species concentration. Like any other variables, the bromine chloride variable is species concentration bromine chloride. So we have to find the variable of methane, and the variables of longitude and latitude are lat and lon. Simply those words are the variables here, and we have to call them, we have to assign them to the file we are processing. This one is the file. So let's not just stress out about the total process. Just catch up that we have to look for the dimensions of the size of the lat and lon, and we have to find out our desired desired variables or desired info of the variables. Then I will go to the I right now know that the variable is the latitude is 91 layers, or the variable of latitude size is 91, and longitude is 144. So in this case, we are here actually defining the variables. So the next step is, yeah, write the ideal codes. So here I am writing the ideal codes. Those are like the informations that we just add in every ideal code. And here is the line that says pro, and then the name of the code. So pro here stands for program, and plot methane concentration 2015 June. And by writing concentration latitude, FLT ARR, it is the floating area where this is the like format of defining a variable. So you can name your variable anything, variable and the type of array, and lon, then lat. So this is only latitude. So we are gonna insert the latitude size, which is 91 from here. The latitude size 91, and the longitude size is 144, which is also floating array. So floating array is kind of a type of arrays. There is also another type, which is double array. I don't actually find any differences between the floating array or double array, but um, for my initial ideal codes, I used floating arrays a lot, and for my later codes or the recent codes, I'm using double array. It actually does not make any difference for me. So you can actually you can see uh, the lat is double here. So you can actually here write dbl. So that will make it double array or FLT, the floating array. So, and we are defining those variables: concentration latitude 91, concentration longitude 144, and the main variable which will combine the total dimensions. Like it's like the matrix or the grid boxes. there is 91 layers. Now, if I can, I think I cannot draw anything in MS Teams. So it's like 144 like longitudinal mm, the 90 actually, yeah, I can like explain it with rows and columns. Here is the latitude of 91, so that means there is 91 rows in the grid box, and there is 144 columns in the grid box. So that makes the total number of grid boxes is 144 multiplied by 91. Did you get that? It's kind of simple. Like, do you understand the size of the grid boxes, or the number of the grid boxes?
Yes.
It's just like the number of rows and columns. The longitudes are the columns, and the latitudes are the rows. So then I will be going to my to set plot device, which is I am defining the format of the file, which is PS, and this device we are assigning color one. I have not paid much attention in those things, but I think I know this is the bits per pixel 32. The more you the more actually it is here in gamma. So you can say this. Actually, it's gamma plotting. Actually, let's not go there. Just understand we just it will be constant for all of the plottings you will be doing. So this is the color one, and bits per pixel 32. That will this 32 number is I think the maximum. So it will come up with a high resolution plot, and we are assigning a file name for our output file. When we are done with this ideal code, we will run this ideal code, and the plot or the final result will come out this in this name, surface methane concentration June 2015 version 1. So why am I putting why am I like using the version here? Because we have to use different settings in one plot to calibrate or to make the plot better. So using versions is really helpful to distinguish or to make like separate settings of plots of the same of the same file. So and then I will I would use the data we are trying to process, that will call input data. You can call it anything. You can call it file. You can call it data. You can call it actually anything. You can call it also a word I. So it will depend on you what you want to call it. Like for this one, I am using input data, and I am you guys understand this like path where we can get this path, right? In my grid, yeah.
Quick question, Devatash.
Yeah.
So you said the output plot will come out as surface CH4 concentration June 2015 version 1. Is that already created, or when you run this IDL code, it'll create this automatically.
It will create this automatically. It's right now not created.
Okay, gotcha. So once you run this, it will create as the output, right?
So okay. Yeah. So when when I will compile this code and run this code, it will come to this line, and it will create a surface methane concentration June 2015 version 1 PS file in this directory. So we have to create up to this directory. So this is my home, and there is this this plot results, you can see. So all of my like PS files are in there. If I go there, so you can see all of my PS files. So when I will run the code, for now, I have already the version 1, I think, the surface one here. The surface methane concentration June 2015 version 1, because I ran this code last night. So I will be changing the version to version 2 right now. So then we will be we will be inputting the file path of the netcdf file we are trying to process. This is this one. Like you want to process this global simulation number 4, 2015 June. So this one, right? Species concentration 2015 June. So I will just write pwd that will give me the file path until output directory, and then I can just copy the file path here like this one, and then / and the file name. So this is like similar. So why this line is red? Because I have inserted a semicolon right in front of the line. So that line will not be read by ideal. So you can see several lines are red. So the color red, and all of those lines have semicolons in front of them. So if we put semicolons, that will not be will not be read by ideal code. So I'm gonna like delete this line anyways. So after inserting the file that we're inserting the pathway of the file that we're trying to process, we have to open this file. So in order to open this file, we first have to assign the file ID, and we have to use the command netcdf open and the input data. You can see in the parentheses, this is the input data. So it's open now, and we are reading the latitude information. We are assigning the latitude into a variable ID here. So var ID means variable ID, and then lat, that is you have seen the latitude variable here. In every variables, here is lat and long only. So you have to find that out. What is the variable of lat and long? So we are defining a variable. We are assigning it to a variable ID, and we are using the lat word to like direct the variable to this variable ID. And we are also using the file ID, because the file ID has the input data, which is the file that we are trying to use. So the format will be netcdf to assign a variable into a variable ID is netcdf var ID, then the file ID, which contains the file we are trying to process, and then the variable for the latitude or longitude. Same thing is for longitude. You can actually write anything here. Var ID latitude, the full name latitude, the full name longitude, but you have to use this lat because this is like predefined here. This is predefined here, so you cannot change that. You have to use this specific lat word to assign it to a variable ID. So, and then we have to also assign a variable ID to the surface concentration to this variable. So here is three variables. This one I'm not just showing the methane one because I have to find it again. So this is just another variable for peroxide, species concentration peroxide. This is one variable, and those are two variables. So for when you guys will, this is now a 2D plot, or yeah, this is now a 2D plot. So when you guys will do a 3D plot or three-dimensional variable, it's the labels. So you can see the labels here. The labels also have sizes. 72 layers. It's the like vertical column layer. 72. There is 72 layers. So you guys will see it if you guys do the ideal plotting continuously. So there is actually those are all variables, but we are using those two right now because we are only concerned in the lat and lon and the species concentration of the species. So after assigning the lat and lon to variable IDs, we have to also define the surface concentration, that is a species concentration methane, into a variable ID. So we have like assigned them into the variable IDs here, and we have to get the variables now. We have to like specify that this lat is 91 levels, this lon is 144 levels, like this one. So we have already specified that. So we will use this one with our variables, like it's saying get the variables. So for latitude, the command will be netcdf var get, so variable get, and the file ID, this one, and then the variable of variable ID of latitude, this one, and the concentration of latitude, which has the like array dimensions or array size of 91. So this one completes the procedure here of assigning a variable into variable ID, and then set the variable size of this variable ID to 91. That's how we can get the variable, like we can finish getting the variable. So first of all, same thing for longitude, var get, then file ID, then the assigned variable ID for longitude, and then concentration longitude. Same thing for emissions. Actually, it will not be emissions, it will be concentrations. So same thing, var get, file ID, variable surface concentration, this one, and the concentration of CH4. So actually we are assigning the variable IDs and then defining the sizes here. So when you use this concentration CH4, it will automatically come up with this size. So we have to like connect between this lon and this concentration latitude. This is the only way to connect with a variable with our with a predefined variable in the file, in the netcdf file, with our own defined variable concentration latitude. This one is not in the file, right? Concentration latitude or concentration longitude. I wrote it. I defined these variables, but I need to connect it to the original predefined latitude and longitude. That's why I am getting the variables here and assigning them to the variable IDs. So you will get this eventually after some practice. And right now we can actually, our code is kind of at the end, but we are trying to convert this concentration from mole per mole to parts per billion volume and into a 2D variable, which is it's already in 2D. So there is only two dimensions here. So longitude and latitude. There is no levels or there is no time. So it's only 2D. So that does not include this. We can omit this line. So to convert from mole per mole to parts per billion, we have to define a new variable, that is ch for new, and which dimension is also 144 by 91. But we will only multiply or divide with the multiplying factor here to like we do this in atmospheric chemistry or air pollution engineering class. Just like one mole per mole is equal to 10 to the power minus 9, right? So this one is important. This is the for loops for ideal codes. So this one for the dimension is 144.91, right? So I is the latitude, sorry, I is the longitude, and j is the latitude, and k, if we use k in future, k will be the levels. So we have to the format sorry, the format for using for loop is it will start from 0 and it will end n minus 1. It will end on n minus 1. So the n is n equal to 144. So it will be 143. The end value of longitude will be 143. Same thing for the latitude, and we are using do begin. So if actually it's saying for I equal to 0 to 143, actually it's saying I when the I is at zeroth row, sorry, zeroth column, there is the longitudes are columns. So when the I is at zero columns, it will start and it will not stop until 143, until the 143rd column. And same thing for the latitude, it will not stop until the 90th row. So for do begin, and then j equal to 0 to 19 do begin, and this one, this variable, I think my ideal just got hung. If do you guys have any questions until now?
Um, I don't have a question at the moment, but you're going to be uploading the
Video.
presentation, the file. I don't know if you uploaded it, but are you going to be uploading the
This one?
presentation? Oh, yeah.
Okay, yeah, I will be like, I will send you guys this through email.
Okay.
Okay, so yeah, and I will also send you the the recording. Okay.
Yeah,
So,
thank you so much.
Thank you.
So
Just quick, just wanted to clarify. The 143 and the 90, that's where the for loop stops, right? That's
yeah,
why.
yeah,
Just wanted to make sure I got that right.
Yeah. So just we can play another. We like you want to define a new variable. We can see ch42 or ch4 and FLT array, which is floating array. Like we can set the we can set actually we cannot set it arbitrarily. It must make sense with the dimensions you are playing with. So let's say 3600 and 1800. So there's the 0.1 by 0.1 resolution. So if I use for loops for this one, so it will be like 0, 0 to 3, 5, 9, 9 to begin. That's the way of using for loop. There is also if loop, if and if, then end if and else. So you'll see those loops or those commands in ideal continuously if you work with ideal. So after defining those, we have to convert the old concentration of CH4, that is this one. So we have assigned this one, right, to our species concentration CH4. That's the one variable ID of surface concentration, and we have assigned it to concentration of CH4. So that's our like right now final variable. If we want to plot a plot for mole per mole in mole per mole, we can directly use it here in TV map. But we are trying to convert the mole per mole into parts per billion. So we'll just multiply it with the 10 to the power 9. So D here stands for the 10 to the power minus. And if we use E, it will like indicate that it's 10 to the power 9. So it's 10 to the power positive 9. And if we use D to the power 9, you know that like 1 mole per mole is 10 to the power minus 9 parts per billion, right? So here that's why we are multiplying this 10 to the power 9, and we are using the end for. So for each for loop, you have to end it with the end for. If I had used like 4 for loops or 5 for loops, I had to use 5 and 4 for that. So for each for loops, there will be end for that. And then it's already this CH4 new is in parts per billion. So we we want to know that the different informations of this CH4 new, like the dimensions and the values in each grid boxes, so that we can make the plot better. And we can print the mean of this CH4 new. We can also print the total, like this one, total CH4 new. And you can also like print any text here. So I want to when I will be printing this CH4 new, it will not tell me that it's the mean. So I cannot tell which is the mean, which is the total. So I can use a text, that is this one, total concentration of CH4, and then it will print this line and then print the total concentration of CH4. Same thing for like I can copy that, and the mean concentration. of methane. And then I would like to print out the concentration latitude, the 91 latitudes, and the concentration longitude. And this is the my city. My city is the color table. So it will plot. It will like make a plot with white, green, yellow, and red. There is also other color codes that you can explore, but I use this code too much: white, green, yellow, red. So that's the conventional like plotting colors. There is also like a green, yellow, blue, red, that type of color codes. So like I like to use this color table: white, green, yellow, red, and the colors will be 240. There is like number of colors, so I don't bother with this line actually, because this is pretty same for all of the plots, and it will I am trying to find out the maximum value of this ch4 new, the maximum value of this variable and the minimum value of this variable. So to do that, just assign just write max data and max, then the variable. Here you have to just change the variable. This one is the format right here, and then print max data, print min data. It will come up with the maximum value of ch4 and minimum value of ch4. So here in the end, you have to use TB to TB to make a plot here. So the format of TB map, I will be sending you the the link of TB map here. I'm gonna show you the TB map routines. You have to understand the TB map routines. So this is the calling sequence: TB map, then data, which is our variable here, then X array, then Y array, then keywords. There is like some useful keywords like isotropic, grid, continental, coast, C bar. So TB map, then data, our data, methane new, then concentration longitude, which is our X array. You know, actually this one is kind of helpful to understand that which way is longitude and which is latitude. So X array is this one, Y array is this one, and then the keywords, the isotropic. Isotropic means that your plot. So you guys can hear me, right? My earphone just got like the battery is dead, right?
Yeah, I can hear you.
So I can switch to my another. Let me just use my other headphones. So I think my PC has some issues with the microphone. Just a second. You guys hear me now?
Yes,
Okay.
I can hear you.
Okay. So this is the data, X array, Y array, and keywords. So the isotropic is the plot. I'm like going to pull out the plot. This one. So, oh, no. So this is the version 1. So the isotropic, isotropic will plot a like the size of X array and Y array will be equal. So this is the plot of the methane concentration, surface concentration of 2005 June. So the dimensions in the latitude. This one and this dimension will be same. The isotropic stands for like you can search here isotropic. So if said it will produce a map with the same scale in the x and y directions. So you just have to read this TB map routines, what this stands for. And this grid is when I write this keyword grid, it will come up with the grid lines. You can see the grid lines here, the grid lines. And continental, it will come out with the continental like uh, boundaries of all over the world. So you have to, if you are plotting a global map or any other map, you have to use the continental. It will like come up with the boundary lines of different countries or regions. And the coast, it will also come up with the boundary lines of the coasts. And CBAR here is color bar. So the color bar is this one. So you are actually defining the you are actually calling the TB map to show the color bar. If I omit this color bar here, it will not show me this color bar here. So I don't want to do that. I want to see the color bar, and I want to also specify the color levels, which is C levels here. You can see 1600 to 2000, 2020. So you can see 1600 to 2020, and the unit, sorry, the CB format. CB format is it's F 12 point something. So if I set 1 here, it will come up with one decimal, one digit after the decimal in the color bar. You can see 1600.0, 6040.0, 6080.0. So we cannot actually omit or make this thing 0. We have to specify at least 1. So when if I pull out any other plotting, like this one, this is the Detroit tropospheric column of nitrogen dioxide from OMI sensor in 2017. So you can see there is 2 digits after the decimal. So in that case, we used F12.2, just that one. And if you want to use 3 digits after the decimal, you can use 3. So I'm using 1 right now because those are only those are not like fractionals. So I'm using this one. And the CB unit, which is the color bar unit, is PPBV. You can see that here. And the CB position. So the color bar position, this one here, is kind of at the middle of the plot, and you can see the format of the color bar position: left, bottom, right, and top. So those are the like distance of the color bar. From left, it's 0.05, from bottom it's 0.02, from right it's 0.885, and from top it's 0.05. So from left, bottom, right, and top. And the title of the plot, which is surface concentration of methane in June 2015. This one, global surface concentration. I think I have edited this one later. So I will be showing you the total process. It will not take long, and this is the total character size. The TCS FAQ is top title character size. So you can see this one. This is the top title. So I can like control the size of this text, of all those texts actually. The top title size and the character size of X levels, X and Y levels, and the color bar. character size for the map levels and XY titles. And this is the thickness of like the boundaries here. Those are the thickness, these boundaries. So you can basically control everything in this plot. And you have then the like procedure of TB map is kind of finished, and you have to close the device now. The device is this one. You have started this device, and you have to close this device. Uh, 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 or it will come up with an ideal error, and you have to use the set plot my device, this one, my device, and you have to end the program. This end, you can either use it all uppercase or all lowercase or any other, just write end. So it will end the program of this ideal code. So I'm going to run this real quick and show you how to like run the ideal code. So first of all, right now grid does not support ideal directly, so we have to use SSH, the free node we are using, YSH1. So it will come up with the same thing, with the same like nodes or same interface, and we have to go to our directory of ideal where our ideal code is saved, which is in GC processing. Oh, actually, I have kind of missed the very initial procedure. How can you like make these pro files in your grid? So before even starting everything, you can just nano and name your file anything like surface concentration methane. So I want this to be peroxide H2O2. Just I have renamed this, and I have used the I have used the command nano, and then I hit enter. So this is a completely blank file that I will be editing in Emacs. So we have to actually make this file. We have to actually create this file in grid HPC to use it in Emacs. So if I close this file right now, it will not be saved because there is no lines in it. So I will write the pro and then plot surface H2O2 concentration. That's how. And control O, you can see there is yeah, control O. If you press the control O, you will save this file as plot surface H2O2 concentration dot profile. So I am hitting control O, so it's saying write plot file name to write this one. So I will be hitting enter, and it's right now saved. So if I exit it by hitting the control X, it will make a file here. You can see February 8th, the time will be saved 13:59 and plot surface H2O2 concentration. So we can also go there by hitting nano plot surface H2O2 concentration. You will see this line only, and you can you can open this in Emacs on the
Hey,
right.
Devitash.
Yeah.
So since we're creating like if we create the file through Nano or Vim, wouldn't we
Yeah.
just be able to write this the IDL code in there versus opening Emacs, or do we have to open Emacs?
No. You don't have to open Emacs. You can write the ideal code here. But like Emacs is really conventional. I also used to use this ideal interface for writing ideal codes, but that's kind of hectic because I don't like get to uh, use different panels or different windows like this one. You can actually open as many windows as you want here.
Oh,
And Yeah, and you can like copy anything from here to there, and you can also clone the ideal codes. So right now I will be opening the plot surface. This is the actually first step. I kind of missed that. Sorry for that. So this is plot surface H2O2 concentration. I will double click on it and it will only show me this one, this line. And right now I can I can start writing the code or just copy the codes and make the necessary modifications for this surface H2O2 concentration. So if I want to make similar plots like this, I will only, because the Latin law is similar, I will only change this one, the species concentration methane. It will be the species concentration H2O2, and I will change everything that has the CH4 in it, and the plot will be similar, but it will plot the peroxide concentrations in 2015 June if I change the variables. So that's actually the first step. So I'm gonna start ideal and show how to compile and run the ideal code. So this is our this is our plot surface methane concentration, and I will try to compile and run this. So in order to compile and run this, we have to call ideal first. So just simply write ideal. So don't bother about this things if it pops up into your grid system. Just write either compile the whole name dot compile, or I use .com, which is the same, the the command for compiling the ideal code. You have to compile the ideal code before running the code. So I will be copying this plot surface methane concentration and hit enter. So it's saying compiled module plot methane concentration 2015 June, and I will be copying this and just paste here and hit enter again. So it will run the code. It's loading the netcdf module. And yeah, it's it's already finished because the code is very simple here. So you can see the different latitudes and longitudes here, and uh, uh, like I have written the lines mean concentration of methane, mean total concentration of methane. So it came with the, like you can see, mean concentration of methane. This one is here, the 1838.17 parts per billion, and the total concentration of methane all over the world in June 2015. It's 2.4 into 10 to the power 7. So you can see the E here. So there's the same E we will be using in our ideal for 10 to the power something. So, and these values are longitude and latitude, and you can see, yeah, it's minus 92 plus 80. So, and these are the compiled modules, and this is the maximum and minimum values of this is printing this line, print max data, print mean data. So the maximum value is 1979 and the minimum value is 1782, and all of the modules are compiled, and we can now transfer. The last step is run the ideal code, get output file and plot as PS, which is ps.ps file format, and transfer it from your PC to and convert it into a PDF. So this is the plot. This is the Globus. I think you all have set it up into your computers or like through the browser. So this is the plot result. Here, all my PS files are being saved. You can see plot results, and the name of the PS file will be surface methane concentration version 2. So I will be looking for S. There is so many files in there, so you can see this one. So this one is version 2 here. When I like hold my cursor in there, it will say version 2. So I have to just click here, and I have to specify the PS folder or any folder that I want to copy this file into. So this is the folder I normally copy my PS files, and we have to just hit start, and you can see the transfer request submitted successfully. So I can see the details. It's success. So it's saying the transfer is completed. So I can go to my PS file folders here and find the surface concentration here. So you can see this is the version 2. This will be the same actually, the same plot, but the title will be different. Here, the surface concentration of methane in June 2015. This one. CH4 in June 2015. So actually, yeah, this is kind of the pretty procedure for ideal plot, the basic procedure for ideal plot. There is, and we can save this plot as PDF by hitting save. If we want to hit save and save as PDF, and yeah, I like try to save my PDF files, the final formats of those PS files, because those PS files are of different versions, and I only save the final versions here as PDFs. So just we can just hit the PDF and we can save it here. So I'm not gonna save it because it's already in there, and I think, yeah, it's pretty it. And yeah, there is always like better ways to improve your code if we are talking about ideal code. So I will be sending out this index that will show different types of codes. You can combine those two netcdf files, even hundreds of netcdf files you can combine in one plot, or you can like specify just 1 year for a range of year, like you have 26 years of netcdf file or 50 years of netcdf file in one file, and you want to measure the concentration of methane in just 2012. So you can do that too in ideal. And ideal is also ideal is mainly for my last project for the premature deaths. Ideal, I have used ideal mainly for big calculations like this one. I would like to actually show you. I know it's 8 minutes past. Just give me 2 minutes. So this one is the PM215 mortality and this mean control. So those are really like big codes, and the same thing, the defining the dimensions, defining the array type, then calling the like the file that we are trying to use or process. So this is just for this is not a plot code. This is just for doing the mathematical calculations here. So ideal can be like really helpful to do different big calculations or to process big data. So I think, yeah, if you guys like, I don't know, like if you guys will work on ideal in a regular basis, but yeah, it's fun. From my end, it's fun. Yeah, I think, yeah, we are 2:10. Yeah, it's 10 minutes past of my time or your time. So I think I will give you guys the files, the necessary files, and this recording. Okay, and let me know if you have any questions. Actually, in while processing ideal, you will face many problems. I normally ask professor about those, or I normally come up with the procedures of defining variables or reversing variables, and ask professor if it's correct. So that's my way of doing doing a different testing different like settings in ideal. So actually it will depend on you how you can use it, but yeah, I am you can ask me if you find any like difficulties in writing ideal code.
For sure. Thanks, Devatash. Yeah, this is honestly really, really helpful. I just had a quick question before we end.
Yeah.
I know that you probably have to get off. Um, your idea, like your process outputs and your like where you like write the IDL code, is that in your like I guess like the node directory that we like call for, or is it like in your like main home folder, like little tilde?
It's in my node. After I request my node for like our group nodes, I
Mm-hmm.
just create a directory here, like
Mm-hmm.
the plot result by the command make directory, and anything the result. So it will
It's not like
make it.
in tier 2, right?
Sorry.
It's not in like tier 2 with
No, 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 no,
where
no,
like our group folders and stuff are, right?
no, no.
Oh.
It's it's now in like in my home, but I have like backed up the different the final versions of the code in tier 2. You can do it actually anywhere. You just have to pull out the right code from right folder. Like here is the tier 2. So I will be going to the homes groups and our home, and this is my common home, and this is the GC processing. So you can see there is also like ideal codes, and if I like pull out any plots, I can do it here. I can do it in my home. It doesn't actually matter.
Mm-hmm. And then if you want to revisit the outputs that like when you ran the IDL code, like the printed outputs, do you have to rerun that all the time, or does it save into like an output folder or file?
Yeah. No, I don't have to revisit it. You just can use the version numbers, so they will be distinguished. And this
Mm-hmm.
is the output file, output folder, plot result. I am specifying this output folder here. Like you can see the PW, like plot result, right? So I am just specifying the output folder here, the plot result.
Oh, gotcha.
So you can see this is the version 22. So I have to run this code around 22 times to get the best result out of it. So that's the like trial and error thing of ideal.
Mm-hmm.
Yeah, and yeah, that's pretty much of it
Okay.
for the beginners actually. And you can be proficient while you practice it a lot.
Mm-hmm.
I will send you this PDF. This is all like different kind of ideal codes that I have encountered.
Mm-hmm.
So you can actually like skim through and try to understand how I have defined the variables, and how like this is the BC like black carbon, two types of black carbon combined, and I'm combining this by this line. I have specified it by yellow line. This is the main line, combining two variables into one variable, just a plus sign. So it's
Mm.
basically the mathematical expressions that we use in our ideal. Yeah, go on.
Yeah.
Yeah.
If it makes, oh,
Oh, sorry.
I was just gonna say, if it makes it easier, you could probably just drop those files into this like chat on Microsoft Teams.
Oh, yeah, sure, sure.
Because I think the recording automatically saves on here, like
Mm-hmm.
once we're if that makes it easier for you.
Yeah, okay. So I will be doing that. I will do that shortly.
And you're going to be putting that PDF, the ideal code PDF on there too?
Yeah, I will share that.
Cool, cool. Thank you.
Okay. Thank you guys. So I will end this meeting now. Okay. Good day.
Okay. Have a good day.
Bye bye.
Bye-bye.
Okay.